So we will see the graphical method to solve linear programming problem. So previous classes we have seen how to uh, model, okay, or formulate the physical problem into mathematical formulation or mathematical model. Then the next task is that to solve that model or to solve that formulation. Then only we can obtain or get the optimal solution. Now, in this lecture, we are focusing about the solution part and the first very basic method, and that method is called graphical method. We will use here and we will find out the solution. So today's lecture, first we will discuss about different terminologies involved in linear programming problem. So what are the terms comes when we deal with linear programming problem and its solution. Next thing is that what is the working procedure, means what are the steps using this we can find out the solution by using the method graphical, okay, method. Now after that we will see some example problem, we will solve that and will obtain the numerical solution, and that is optimal solution. Then last is a practice set where I have included few questions for your practice, okay, to get confidence on that. So let us start the lecture. That is first, you'll see the terminologies. The first term we will see that solution. What do you mean by solution of the linear programming problem? So the set of decision variable xi, that is I runs from 1 to n, okay, which satisfy the constraints of the linear programming problem is said to be the solution. So if you remember, last class we have discussed about the objective function, decision variable, constant. Now you see, if I have objective function f of x equal to c1 x1 plus c2 x2, so this x1 and this x2 are nothing but your decision variables, okay. Now we have two variables, so this variable or this combination of this x1 x2 will be the solution of linear programming problem if it satisfy the constraint. It is very important, like if we have constant s1 as maybe let p1 x1 plus p2 x2, which is less than equal to d1. That means we have to take uh, the combination of x1 and x2 such that this combination, that is p1 x1 plus p2 x2, less than the value or less than equal to the value d1, okay. Then only that combination x1 and x2, okay, will be the solution. Now here it may be one uh, one constant, two constant, okay, three constant, like that we may have more number of constants, but this combination, that x1 and x2, should satisfy all the constants, okay. Then only it is eligible for the solution, okay. As I have told, we will get a set of solution, so then it is eligible for that set of solution, means it will belongs to that set, okay. After that we will see the optimal one. So those things we will see later. So first we have to understand what is solution. Similarly, here I have taken x1 and x2 two decision variable. We can have more, means three or more decision variables. Okay, but when we discuss about graphical method, we mainly concentrate about maximum two variable, because three variable and more than three variable will be difficult to visualize through graph. Okay, and the main uh, theme of the graphical method is that to see the solution through graph. Understand? Now next we will see what is the second term which will be frequently used. Now in addition with this, you see, first was solution. Okay, first was solution. In addition with this, we have extra thing, that is feasible solution. Means when the solution is called feasible, that is very important. See, the set of decision variable xi, that is I running from 1 to n, means n decision variable may be there, which satisfy the constraints as well as the non-negativity conditions, that is xi greater than equal to 0. You can remember last class we have seen the last condition is that xi greater than equal to 0, means like the items number of products or the number of person, okay, resource, those things will not be negative, it will be non-negative. Okay, so it is the solution will be eligible for feasible solution only when it will what satisfy extra the non-negativity condition. Here you can see the in the solution x1 x2 may be negative value, okay, which satisfy constant, but here only we will take all the positive decision variable, okay, which satisfy the constraints. Okay, now it is clear. What about feasible solution? That if feasible is there, then what do you mean by infeasible? So infeasible solution should be there. So the set of decision variable which do not satisfy all the constraints, you see, which do not satisfy all the constraints as well as non-negativity condition is complement of this feasible solution. So both it will not satisfy constraint, non-negativity condition, then it is infeasible solution. But if the solution will not satisfy non-negativity condition, it is named as solution. That's why it is said that when both, like all the constant and non-negativity is not satisfying, means it is infeasible solution. So we will see when we will solve different problems, we will see different situations where feasible solution will come, where infeasible solution will come, where only solution will come. Okay, is that basic solution. What do you mean by basic solution? You can see that some problems we have m number of equation and n number of variable. For example, here I can write if you have the constants such as like maybe c1 x1 plus c2 x2, okay, so this is one problem which is maybe this equal to maybe t1, then c3 x3 plus c4 x4 equal to t2. Okay, so this is there. Then here you can see what are the number of equation, that is m. So m equal to 2, n equal to 2. Now for example, if I write c11 x1 plus c12 x2 plus c13 x3 equal to t1, c21 x1 plus c22 x2 plus c23 x3 equal to d2. If this is the case, now tell me how many equations are there. So here you can see m equal to 2. Okay, so I am writing here m equal to 2, and what about n? N equal to number of variable x1, x2, x3. So 3 variables are there. So in this case what happens? So consider the set of m simultaneous equations with n variables. That means n greater than m. So in this case, okay, when this type of situation is there in the linear programming problem, then the solution obtained by n minus 1 variable equal to 0, and solving remaining m simultaneous equation with m variable is called basic solution of the same. Okay, just you see the solution by obtaining so the solution obtaining or obtained by taking n minus 1 variable 0. So for this case, if I am writing, if I will write, you see what will happen. If we take, means let we take x3 equal to 0. If x3 is 0, then that equation transformed into C11 x1 plus C12 x2 equal to D1 C21 x1 plus C22 x2 equal to D2. So this is a system of equation. Now the solution of this system of equation. So whatever be the solution of this system of equation, whatever is the solution of this system, okay, now the solution is called basic solution. You see here it is written basic solution. I hope you understood. The variable which contribute the basic solution are called basic variable, and this x1 and x2 are contributing. So this x1 and x2 are contributing, okay, for the solution. This is called basic variables. Okay, we can write here x1 and x2 are basic variables. Clear? What is basic variable? What is basic solution? Now the variables which contribute to the basic solution are basic variable, whereas the n minus 1 or n minus m, n minus m means here n is 3, m is 2. So one variable which we had x3, this one, that do not contribute to the basic solution is called non-basic solution. So x3 is non-basic solution. Okay, clear? So when we have simultaneous equation, and where equations are less than number of variables, when equations are more than number of variables, that time it will be difficult. Okay, but if number of equations or simultaneous equations are less than the number of variables, then this case will come. Then what we can take? We can take some of the variables as 0, and those variables we are considering as non-basic solution. Sorry, non-basic variable. It's a non-basic actually variable. Okay, and those are contributing to the solution, that is called basic variables. I hope it is clear. So next we are going to see addition of this, means basic feasible solution. First we know what is solution if it is satisfy constraint. What is feasible solution? If the solution satisfy, if the decision variable satisfy both the constraints and non-negativity condition. Another thing is that now we are adding basic feasible solution. So a basic feasible solution that you have to see. So a feasible solution of a programming or linear programming problem which is a basic solution, understand what I'm saying, means the solution what we are getting after taking the extra variable as 0, called a basic feasible solution. Clear? In other words, we can say that we may say the basic feasible solution satisfy the non-negativity condition. Okay, basic feasible solution also satisfy the non-negativity condition. These solutions are of two types. So what are the two type of solution again? See, basic feasible solution again divided into two types. Okay, depending on the x3 nature, that extra variable. So first is called degenerate. So degenerate means if at least one basic variable is 0. Here you can see we got x1 and x2 as basic variable. Just think about if our solution is, means solution set is x1, x2, x3. Clear? Where x3 is 0. Now 1, 2, 0. This is one, consider this as, maybe assume this is one solution. Now out of this, for example, x1 and x2, if any one of them is also 0, like if you take 1, 0, 0, so this case will be what? This case is called our degenerate. If at least one basic variable is 0, okay, all is 0, fine, but at least one is basic variable is 0, then it is called degenerate. And if all the m basic variables are non-zero and positive, understand, like in the first case 1 comma 2 comma 0 I'm taking, so 1 and 2 both are non-zero as well as positive, so in that case it is degenerate. Okay. So one is, sorry, in that case it is called non-degenerate. So one is degenerate when at least one basic variable is 0, so degenerate basic feasible solution. Another is non-degenerate basic feasible solution, means when all the m basic variables are non-zero and positive. I hope it is clear the terms which we will go to use when we will solve the problem. Next is what is optimum basic feasible. Okay, basic feasible solution we know. Now next we are going to see optimum. Optimum means the best one, either in terms of minimization or in terms of maximization. So a basic feasible solution that optimizes, means minimizes or maximizes the objective function, is said to be an optimum basic feasible solution. Okay. Next is unbounded solution. So sometimes solution will be bounded, sometimes it will be unbounded. Means the set of solution you are getting. Sometimes you can find, okay, all the solution are confined in a particular region, or sometimes you will see that the region is unbounded, so that the solution what you are getting, it's coming and coming after, like if you are finding maximum of that, then maximum each time you are finding it is maximum. Okay, so in that case it will be unbounded solution. We will see through example problem, will illustrate that a solution that decreases or increases the objective function value is called unbounded solution. Okay, next is our working procedure, how this method will work. So this method will work using three steps. One is your formulation of the given problem as a linear programming problem. So that already we have seen. The modeling part means how the physical problem can be transformed into a linear programming problem using your mathematical model. Okay, using your mathematical techniques. Okay, that thing. Next thing is that after getting the linear programming problem, step two is to plot the given constraints as equalities. Here it is very important. The constraints will be in terms of what? Three things I have told. Either it is in equal or less than equal or greater than equal form. Sorry, not zero, some value maybe maybe q. This is maybe r. So this will be there. Now all these things, whatever it is there, we have to convert into equality form. Okay, means what we have to write? Ax1 plus bx2 equal to 0. Okay, then like this. Okay, we have to write. Then we have to determine the convex region formed by the equality. So what do we mean by convex region? I am saying, you see, if you take like this one region, okay, now convex region means that if this is the inside region, okay, now if you take any 2 point in between, then the line segment between these two, okay, point should completely lie within that region, then it is called convex region. For example, if you see this one, okay, region, okay, now in this region if you take here one point, here another point, and if you join, you see the line segment between these 2 points, what we are getting, okay, half is inside this, okay, region and half is outside the region, which is not there in the region, then it is not convex. Okay, This is convex. Clear? Now convex region may be this triangle also convex. Okay, if you can take square. Okay, if you can take any trapezium also, this is also convex, because any 2 point you can take in between, mean any 2 point you can take in this region and draw the line segment between these 2 points. Okay, then that will completely lie within the region. Okay, so that is there, the convex region. So plot the given constraints as equality on x1 and x2, as we are dealing with two variables, because that will be easy to illustrate through graphical method. Okay, so if two variables are there, so first you have to convert the constraints into equality form, then you are trying to get the convex region of that. Okay, then from the convex region we will get the solution. So third part is, you see, third step is find the vertices of the convex region and investigate the value of the objective function at each vertex. If this is the convex region you are getting, so find out the corner points or the vertices of this convex region. Okay, and that corner point or vertices, you have to find out the function value or objective function value. Okay, from that you will see which value is giving minimum, which value is giving maximum. So the set of or the particular vector which is giving function value as maximum for maximization problem, that will be the optimal solution. For minimization problem, if the particular vector v is giving minimum value for the objective function, then that will be your solution for that minimization problem. I hope it is clear, the three steps. Now we are going to see those things, but before that some points are there we need to discuss. First, the collection of all feasible solutions to a linear programming problems form a convex set. Understand here, all the feasible solution form a convex set whose extreme points means corner points, what I have shown just now, correspond to the basic solution. Okay, now a convex set is a polygon in which if any 2 points are selected arbitrarily and a straight line segment is drawn, then the line segment lies completely within the polygon. Just now what I have shown you, that convex set, what is convex set, what is convex region, and polygon means, like if you are telling, if you are getting triangle, so okay, then next is your quadrilateral. Okay, so if dimension increases, okay, depending on the number of vertices, then it is said to be polygon. Okay. There are finite number of basic feasible solutions within the feasible solution space. What do we mean by feasible solution space? Means the set of feasible solutions is called feasible solution space. Okay. Next, if the convex set of the feasible solution, which constitutes of equality, simultaneous equations, and non-negativity condition, is a convex polyhedron. So names are different. Okay, just see the name, it is important. Polyhedron is there and convex polyhedron. Then at least one of the extreme point gives an optimal solution. Okay. If more than one extreme point give optimal solution, it may happen that you can see there are multiple points where you will get the same value, and that is the optimal solution. Then the value of the objective function will be same for all the convex combination of the extreme points. You just see, maybe this is a convex region, okay, and this is A and this is maybe B. Both A and B, the z of objective function z of A is equal to z of B, and this is our optimal solution. Okay. Now this A and B are optimum solution. Okay, this combination of x1 x2 whatever is there. Now, if you see in this convex region, okay, this is a line segment between A and B. That means if you take any other point in this line segment A and B, it will give optimal solution. Okay, I think it is clear now. Next, we are going to see about some examples. So here I have added 6 example problems for easy illustration and to understand what are the different type of solutions we are getting, bounded, unbounded, okay, depending on the number of constraints, depending on the type of constraints. So all those things we are going to discuss in detail here. Now example 1, what it says, it says that the maximizes z equal to 3x1 plus 4x2. So if you see, this problem is nothing but the problem which we had discussed yesterday for the first modeling problem. Okay. Now this is subject to 4x1 plus 2x2 less than equal to 80, 2x1 plus 5x2 less than equal to 180, x1, x2 greater than equal to 0. Okay. So first of all, what to do? We have to convert these constraints to equality form. So from here, what we will get? We will get a straight line, that is 4x1 plus 2x2 equal to 80. Clear? Now second one, we will get 2x1 plus 5x2 equal to 180. Okay. Now you can observe that equality we have taken, but the solution, all the solution lies between this, where to where? X1, 4x1 plus 2x2, we have to take x1 and x2 in such a way that the combination, so that 4x1 plus 2x2 less than equal to 80. That means if we draw the straight line, maybe this straight line, then the solution will lie here below region. Okay, because less than equal to sign, if more than, greater than equal to sign, above, okay, above 180. But if it is but here it is less than equal, that means combination of x1 x2 we have to take, so that it will lie below 180. And another restriction is that all the x1 x2 will be positive, means we can take x1 x2 0 0. So if I take 0 0, then it is satisfying. If I take here also 0 and x2 0, it is satisfying. So 0 0 is one also considered. Okay, so that thing you have to keep in mind, these three. And then we have to create the region, we have to make the region. Now we will see how we can do. Okay, so first is this, we can find out 4x1 plus 2x2 equal to 8. So we have equation 4x1 plus 2x2 equal to 80. So how to plot? So to plot or to find out the line, okay, or equation, what to do? We need 2 points. Okay, if we have x1 and x2, then if we have 2 points, then we can draw a straight line to find out 4x1 plus 2x2 equal to 80. Now what I can do, if I put x1 as 0, what will be x2? 2x2 is 80, so x2 will be 40. So this is one set of point we can get 0, 40. Now second case, what to do? x2 if I take 0, then what is x1? 4x1 equal to 80. That means x1 equal to 20. So one point is we are getting 0, 40, okay, and another point we are getting 20, 0. So using that we can draw a straight line. So 20, 0 is this point and 0, 40 is this point. Now we can draw the straight line. Similarly, second equation, what we had? 2x1 plus 5x2 equal to 180. So here we can draw, or we can find out 2 points, that is we can take x1 and x2, x1 first as 0. If I take x1 0, so 5x2 equal to 180. That means we will get 36 x2 value. Second is if I take x2 0, then what is x1? x1 is nothing but 180 by 2, that is 90. So 2 points we are getting. One is 0, 36. Another one is 90, comma 0. So these 2 points we are getting. So we can draw that the 90 0 is this and 0 36 is this. Okay. Now after doing that, we will see what will be the region. So first, for the first straight line, what we have to find out this x1 and x2, or we have to see the x1 and x2 combination so that it will be less than 80 and x1 greater than equal to 0, x2 greater than equal to 0. So this is the region where we are getting. Okay, and these are the region. Okay. So this region you are getting when we take x1, 4 means 4x1 plus 2x2 equal to 80. Now if I take the second equation, okay, if I take the second region, sorry, second equation, that is this 2x1 plus 5x2 equal to 180, then the region for this is this. Now what we have to take? We have to take the intersection of this. We have to take intersection of this region. So intersection of this region is this. For this case, intersection region you have to take. So this is the intersection region. Okay. That means OABC. So OABC. Okay. This is the intersection region what we have. Okay. Now if you see, this region is nothing but the convex region, because if you take any point, any 2 point in between or on this region and draw a straight line, it will be in or on the region. Okay, that's why it is a convex region. Now the end points are what? This is one end point, this B is one end point, O is one end point, A is one end point. So O, A, C is easy to find out, but B how to find out? By solving B. For B we have to solve, if this is equation 1 and if this is equation 2, so we have to solve 1 and 2. After solving 1 and 2, whatever x1 x2 you will get, that will be your B, and that will come as 2.5 and 35. Clear? So this is the point. So next task is that whatever be the Z, so Z I think we had 3x1 plus 4x2. Okay, now what we can do, we have to first find out the Z value at O. So Z value at O means 0 0. So 0 0 if we put, then Z value is 0. Now Z value at A we have to find, that means 20 into 3 plus 0 into 4, that is 0, that means we are getting 60. Okay, similarly ZC we can find, so ZC equal to 0 into 3 plus 36 into 4, we'll find out what is that, and ZB also we can find out. Then we will see where the Z value is maximum, and the corresponding that point is the solution. So we will see that here. Here you can see Z0 is 0, ZA equal to 60, ZB equal to 147.5, ZC equal to 144. So which is the answer? This will be the answer, ZB, and this will be the optimal solution, optimal answer. So B is the combination which we need, that is when x1 is 22.5 and x2 is 35, then Z will be the maximum. So here one thing you can note, that mathematically when we do, we can tell, okay, 2.5 material or 2.5 model, but physically we just we need to round up. Okay, but as you are doing mathematically, you just keep all this, you just keep this answer as it is. So the answer is 2.5, and product, and like per week we are finding. So per week if you are 2.5 m1, okay, 2.5 m1 and 35 m2, okay, no problem. If we are taking per 2 week, then it will be then automatical round of 5 m1 and 70 m2. Okay, so this thing you can do. I hope this example 1 is clear. Now let us move towards the second example, which is little different. You see here the difference is that is it less than equal to 30 constant, another constant is greater than equal to 0, 0 less than equal to y less than equal to 12, 0 less than equal to x less than equal to 20. Now what to do? From here the first equation I have to convert it into x plus y equal to 30. Okay, now this will be x minus y equal to 0, or simply x equal to y. From here what to do? One is 0 less than equal to y. So from here we can write y equal to 0, means y should be greater than 0. So accordingly we have to get the region. Okay, another is y less than equal to 12. So from here we can get y equal to 12. So we have to see the region for this, means y value greater than 0 and then y value less than 12. Okay, the next one is here your x value, okay, it's greater than equal to 0. This is a not, this is nothing but non-negativity condition. Here x greater than equal to 0, y greater than equal to 0. So from here you can find x equal to 0. Then x less than equal to 20. From here you can find x equal to 20, and below to that we will consider the region. So you can see how many equations are there. 1, 2, if you consider non-negativity also 3, 4, then 5, 6. So 6 equation we have to plot. So we know how to plot. If equations are like this, then we can take one variable as 0, we can find out other variable, we can take other variable as 0, then we can find the first variable. Okay, like that we can find out the point. If you do that, you will see this type of diagram. You see, first is if we have x equal to 0 above that, okay, above that this region, okay, this region above that, get y greater than 0 this region, okay, then y less than 12 this region, okay, x less than 20, so this region, okay, so those things are there. Then x minus y equal to 0, that means x equal to y if we have taken, then less than equal, less than sign is there. So if I have less than, then what will happen? This will be this region, like that will go. Then another is y minus 3 is less than 0, sorry, greater than 0. You see, 30. Okay, y plus x plus y less than equal to 30. So this region, find out all these things. So x plus y equal to 30. So below to that region we have to see. So below to that region is this one. Maybe I will write down this with this color. So all the domain you have to see. Then you have to find out the intersect. Okay, you have to find out the intersection region, that means common region. So this is the common region we are finding. Okay, this region. Okay, so this is the optimal. We have to find the optimality from this. Okay, now the endpoint are, these are the endpoints that we have to find directly or by solving these equations, like a b c d. A, if you want to find, then you have to solve this equation, that y equal to 3 and this x equal to y, then you will get a equation, this and this, it will give a equation, a point. B, how to find b? X equal to 12, so this one along with this. Okay, you have to find, then you will get this b point. Similarly c d e, you can find. After finding this a b c d e vertices, you have to find out what is za, what is zb, zc, zd, ze, and where your answer is what? Minimization problem, maximization problem. So where the answer Z is maximum. You see here we have discussed now. So the saddle region A, B, C, D, E are: A is 3.3, B is 20, C is 20, 10, D is 18, 12, and E is 12, 12. Accordingly, we will find the Z value, because Z is given 2x plus 3y. So we will find out. So z equal to 2x plus 3y. So za will be what? 2 into 3 plus 3 into 3. So it will be 15. Similarly, zb is what? 2 into x value is 20. So 2 into 20 plus 3 into 3. So 2 into 20, 40, plus 9, 49 will be the answer. And then zc you have to find. Zc is 2 into x, x is 20. Here this is x 20 by 20, 10. So 2 into 20 plus 3 into 10, we will get 30 plus 40, 70. Similarly, you can find zd 72, ze 60, and you can see that zd is 72. We are getting the highest value here. So which is responsible due to D. So D will be the solution. Then 18, 12 will be the solution. If the x1 variable, if the decision variable x1 is 18 and decision variable x2 is 12, then we will get the optimal solution. Then we will get the maximum profit, or whatever we have the objective. Okay, clear? I hope. Similarly, next example we can see. So these are the given problem. From physical problem, we have to convert it into mathematical model, that I am not going to discuss right now, because already we have discussed. You can refer my previous lecture, there it is available. Okay, so just I will discuss about how to make convex region and what are the different solution, and out of that how to find the best solution. So this is the product, and we are going, and this is the problem that we are going to solve. And find it graphically, the number of days for which each plant must run in June to minimize the operating cost and those things. Now if we formulate, we will get minimize z equal to 6000 x1 plus 4000 x2. Okay, and the constant is this: 6000 x1 plus 2000 x2 greater than equal to 80,000. That means if we convert, if you simplify it, it will be 3x1 plus 4x2, 3x1 plus x2 greater than equal to 40. Similarly, second one, the simplified equation will be x1 plus 2.5 x2 greater than equal to 22, and third one is x1 plus x2 greater than equal to 40 by 3, and the non-negativity condition is x1 comma x2 is greater than equal to 0. Now we have to convert this constant to equality form. So first one will be what? 3x1 plus x2 equal to 40. The second equation will become x1 plus 2.5 x2 equal to 22, and third equation becomes x1 plus x2 equal to 40 by 3. and all you can see greater than equality sign is there. If greater than equal sign is there, then you have to take the region above to the equation. Okay, if you do that, this will be our the final diagram. You see, this is 3x1 plus x2 equal to 40. So above that, this region whatever we have, then 3x1 plus 3x2 equal to 40 means the region will start from here. So here it will go, okay, move. And third equation is x1 plus 2.5 x2 equal to 22. Then this equation we have, okay, sorry, this region we have. So common region is what? Intersection region is nothing but your this C, B, A. Okay, and you can see that this region goes and goes. Okay, you don't have any upper bound. Okay, lower bound is there because C, B, A is there, no? So for this case, if we have minimization problem, we can find out the minimum value. But if you are finding maximum, how far you will go? Where is the end? End is not there, so maximum we cannot find. But what problem demands here, you have to see. Problem is say minimize z, so we can find out minimize z. So if you see, then the extreme points or the corner vertices are A, B and C. Now A we can solve from this x1 plus 2.5 x2 equal to 0. From this equation you can find, so x1 will be 22 and x2 will be 0. Similarly, B we can find by solving x3x1 plus x2 equal to 40, this equation with x1 plus 2.5 x2 equal to 20. Okay, intersection point of these two equations will be B. Similarly, C we can find from this 3x1 plus x2 equal to 40 from this equation. So here the C point will become 0, 40. Okay, now we will see those solutions now. So A we got 22, 0, B we got 12, 4, C we are getting 0, 40. Now when we are applying this A, B, C value in the Z, what is Z here? You can see Z is this 6000 x1 plus 4000 x2. Now when we are calculating ZA, 6000 into 22 plus 0 into 4000. Similarly 6000 into 12 into 4000 into 4, like 6000 into 0 plus 40 into 4000. So C you will get at C Z value you will get. So if you solve, then you are getting ZA is 132,000, ZB is 88,000, ZC is 160,000. So which is minimum here? 88,000 is minimum. And for what value or for what vertex it will be minimum? B vertex, that is 12 and 4. X1 value is 12, X2 value is 4. So when we have the decision variable x1 as 12 and x2 as 4, then we will get minimum value. So the minimum value of Z is 88,000 and it occurs at B. Okay, that means x1 we are taking 12 days and x2 you are taking 4 days. Then only the cost will be minimum. I think it is clear. Now next problem we are going to see. This is again a physical problem is given. We have to convert this physical problem to mathematical model. If you so this will become like this. Maximize Z equal to 100x1 plus 40x2, where the constants are 10x1 plus 4x2 less than equal to 2000, 3x1 plus 2x2 less than equal to 900, 6x1 plus 12x2 less than equal to 3000, and the non-negativity condition. So first we have to convert this into equality form. Then we have to see the less than equal sign, means we have to see the region below to this equation. So if you do that, and after getting the common region, we will have the common region 0 means OABC. So OABC is the common region. You can find the corner point, that is O, A, B and C by solving equation. You can get few points, few vertices such as B. Okay, so after getting this thing, you can check at O, A, B, C what are the solution. Okay, Next, example 5. Example 5 is, you see here, maximize z equal to 2x1 plus 3x2, but the constants are different sign, you see, means different inequality. One is x1 minus x2 less than 2, another x1 plus x2 greater than equal to 4. Okay, so accordingly you have to take the region. Now if I plot this, and if I, this is the region. Okay, so the region goes up. Okay, that means it has left, or it has lower bound, but upper bound is not there for this region. So in this case, what we are finding? Maximum we are finding. So maximum we are finding means we will get unbounded solution, because you can see at B and A you will get some solution, but that is not maximum. If you see all other point in this region, it will be more. So more and more you will get if you go up and up. So the solution space satisfying this 2.3, this constant, and 2.44, sorry, 2.43, 2.44 and 2.45, it is seen that there are no common point x1, x2 lies in both the shaded region, and hence the problem cannot be solved. Since the constants are inconsistent, the solution does not exist for this LPP. Clear? Now we get this type of solution. In this case, you will get this type of solution. Below, sorry, in this example 6, you will, if you will get this type of solution, okay, like one is this shaded region, this another is this shaded region, and there is no intersection of the shaded region, then what will happen? Then you will have no solution. Okay, so I have quickly discussed this 5 and 6 example. You can see from the slide here.